So yeah, hi, my name is Kaushal. So today I'll be presenting on our implementation of a graph neural network for three-dimensional object reconstruction in liquid argon time projection chambers. So I'll be presenting on behalf of the UChicago DSI and the Exatrix project. But before I get into the specifics of our implementation, just to give some background, to first start with motivations. So liquid argon time projection chambers are the detector technology for modern high-precision neutrino experiments. Examples include DUNE and microBoon. So within these experiments, machine learning approaches have been proven successful for reconstruction, especially for particle identification. Though typically a lot of these approaches are based on convolutional neural networks, or CNNs, which treat detector data as images and also typically require downsampling of information to fit into memory requirements. So the reason why we're really interested in GNNs is that the large TPC detector data is also very naturally sparse. So by sort of natively translating that data into graphs, we can leverage full use of the information without downsampling by inputting all that in a GNN. So in this presentation, I'm going to present sort of our original design for our graph neural network meant for particle identification and 3D reconstruction. And then I'll also talk about how we were able to leverage the use of 3D context information in order to vastly improve performance. And to give a quick rundown of how we're going from our large TPC output to our GNN input, if you can look at the diagram on the right-hand side, basically each interaction on each plane corresponding to the waveforms on the U, V, and Y planes are each going to be transformed into a graph where each hit is a node and edges are formed between nodes in a certain region or window based upon a determined wire and time tick rectangle. So just to clarify, basically one full interaction is going to give us 3 separate graphs for the neural network to train on. So we want to find ways to design a neural network, and specifically a graph neural network and its inputs, in order to recognize different particle topologies within these interactions. And to get a better idea of what the original GNN classifier looked like and what's going in and out of the model, on the left, you can see an electron neutrino event. On the right, you can see a muon neutrino event. So basically, the original GNN model was an edge classifier. So in this top row here, you can sort of see the inputs going into the model, and then this is the model's attempt to classifying this. Originally, we had 4 classes: hadronic, muon, and shower, hadronic corresponding to the Schur proton track, muon to the muon track, and shower to the electron shower. We also had a 4th class called false, which is basically a non-physical class where a false edge was an edge that connected 2 hits that had different parent physics phenomena. So now, in order to sort of move to using this GNN in more realistic situations, we also had to update our classification and labeling, as well as we changed our edge classifier to become a node classifier. And the way we sort of made that change, I'll explain as well. So basically, we moved from classifying edges to classifying nodes. And specifically, we moved from just 3 hit categories: hadronic, muon, and shower, to 8 hit categories, which you can see labeled over here. In addition to this, we introduced 2 new labeling schemes: a simple scheme, which basically merged these 8 categories into 5 classification targets, as well as a full scheme, which merged these 8 categories into 7 classification targets. So this was done in an attempt to make the model more useful in predicting more realistic and more complex topologies. And you can sort of see the stark difference this has on these new visualizations. So in the top row, you can see our muon neutrino event and our electron neutrino event on the right, as well as you can see more complex topologies in the bottom, where having that more precise labeling scheme is a lot more helpful to understand what's going on in the event. And also something to keep in mind is that these visualizations you see here have no graph structure. As you can see, they're just all at the 2D hit level per plane. And speaking of which, so now to sort of get into the message passing mechanism and the GNN structure. So first, I just want to really give a quick rundown of GNN message passing and how it works in this network, and why it's so powerful. So on the left, you can sort of think of this graph as our initial state. So each node in the graph is going to have associated node features, such as hit position and amplitude. And we can explore what happens to information in this initial state as we see how information from this blue node diffuses throughout the graph after n message passing iterations. So we can sort of see what's happening is that after one message passing iteration, this blue node will propagate its information to its neighbors. And after a second message passing iteration, those neighbors will then propagate the same information to their neighbors. So what's really powerful here is that after just two message passing iterations in this example graph, we can see information from that top left node has already propagated throughout the entire graph. And it's this sort of mechanism we'll be relying on to give us our classification power in this network, and how this sort of portrays itself in the structure. So in this schematic here, this is sort of the design of our original GNN. So we have our input graph, which goes through an input network to get sort of a hidden embedding of the features. And then we have these message passing blocks, where the output of each block is going to be a set of class probabilities for each of the nodes. Now, specifically in our case, the original design did this 4 times until eventually we have our final softmax layer to get a set of class probabilities. And now to sort of zoom into what exactly is going on in this message passing block. So we take advantage of both an edge and a node network. Basically what that means is in this message passing block, what's happening is that first, we concatenate the features between incident nodes on an edge to create new edge features. We then allow the model to sort of learn these edge features to make edge weights. So we put that through a linear model to get sort of a new set of edge weights. And then using those new edge weights, we inform new node features, basically for incoming edges, outgoing edges, and we also concatenate that with our original node features as well. So taking basically these 3 pieces of information together, we also let the model put this through a linear layer and then sort of get new informed node features. So basically, the message passing part of this is by pulling in incident nodes from an edge. We're allowing context information from a node's neighbor to get pulled into this edge, and then we then use that same informed context information from these edges to then get new node features. So that's basically how the message passing is traveling through the network, by taking advantage of the fact that we're training edge weights as well as using those same weights to inform new node features. And then we sort of repeat this process in this message passing block 4 times. So now to sort of talk about graph creation in our network and sort of one of the pitfalls of how sort of a window-based edge forming scheme can be detrimental to the model. So on the slide in the left is sort of a diagram of where we have interrupted connectivity in our graph. Now, in this specific situation, this example is due to unresponsive wire regions, but the reason why we care about this is because of how the message passing mechanism works on the right, which is that even though like in reality, we want this blue track, in reality, this blue track should be completely connected. Because of this unresponsive dead wire region, what happens is that since we so heavily rely on this message passing mechanism, information from sort of this left-hand side of the graph will never travel to the right because of the fact that with message passing, disconnected components of our graph will never be able to talk to each other, which becomes an issue because then it's harder for the models to sort of get greater context information of the entire graph. Now, the interrupted connectivity, as I said before, here is due to an unresponsive wire region, but it's also not limited to just this case. As you can see, the electron shower over here is also disconnected, as well as in more extreme cases with diffuse and cosmic activity, we'll have sort of the same issue. So in order to sort of mitigate this effect, we really want to be careful about how we draw our graphs themselves, which is why in response to this problem, we tested 4 different edge forming schemes. So we have our original window scheme, which connects nodes within a certain time tick and wire window. We also tried a Delaunay edge forming scheme, which computed the Delaunay triangulation of all nodes in the graph, a KNN or K nearest neighbors approach, connecting nodes with its K nearest neighbors, as well as a radius approach that connected all nodes, connected a node with all neighbors in a certain radius, which is equivalent to the window approach, except instead of a rectangle, we have a circle. And to sort of give a quick breakdown of what our dataset statistics look like at this point, as well as how our labeling schemes and edge forming have affected the data. So one thing to clarify is that the number I've cited with the graphs is that one full interaction translates to three graphs per plane. So to just get the number of interactions that we're actually working on, you can just take a third of the number I cited. In addition, something to point out with the class breakdown across labeling schemes is that the the muon and shower hits comprise like a large majority of our hits. In addition, you can also sort of note just the average edges across the edge forming schemes for your own curiosity. So now that I've described the 2D model, I just want to get into the results. So I'll show a table, and just to give a quick summary of what the table is going to tell you, we'll have 8 different total model configurations where we have 4 different edge forming schemes and 2 different labeling schemes for each of those edge forming schemes. So I want to sort of point your attention to the results outlined in green, which are our best performing results in 2D, which come from the Delaunay edge forming scheme, which perform the best for both simple and full labeling schemes. Other things you can notice is that the full labeling scheme consistently performs worse, which is clear when you consider that the unmerged classes, since the classification target for the full labeling scheme is larger, and based upon the data statistics I showed in the previous slide, the unmerged classes also have much lower representation as well. Now, I've also cited something called the consistency metric. Now, what this metric is, and I'll explain it in more detail, is that basically since we have information from the U, V, and Y plane as inputs into our model, a natural question to ask is when we're predicting hits on the U, V, and Y plane, since they're associated with an actual 3D interaction, can we find a 3D representation that basically tells us, are we predicting across each of the 3 planes consistently? And the way we do that is with the introduction of 3D space points. So really, we have the question of how do we leverage all 3 views, and the fact that we know that the U, V, and Y plane all correspond to this one full interaction. So as I just stated, while having access to 3 different views of an event, the model does not actually leverage this information. So in order to sort of get this consistent 3D representation, what we actually do is introduce the use of something called 3D space points. Now, a 3D space point basically connects at most 1 hit from each plane, being the U, V, and Y planes. And now the specifics for how this representation was calculated was, if you can take a look at the citation here, but it was used by using the space point solver algorithm to basically output these 3D space point representations. And now what the consistency metric measured on the previous slide was that basically when our model makes our predictions on the U, V, and Y planes, we ask ourselves, is the prediction across associated hits the same? So a consistent representation is basically, according to the association given by this 3D space point, yes, this is consistent because on the U, V, and Y plane, the prediction was all MIP. However, an inconsistent 3D representation is if even just one of those hits is classified differently than the other associated hits. So the consistency that was cited earlier was just basically what percentage of space points were consistently predicted. And to keep in mind that a consistent representation has to be fully consistent. So how do we implement this within the model itself? First, we package all 3 planes into one object. So instead of just inputting graphs, we now inputted a full interaction to the GNN. And additionally, now we have the power of using 3D space points to connect our 2D representations. So we moved from using sort of a 2D representation concerning the U, V, and Y planes that were separate and parallel to giving 3D context information that allows the model to recognize the fact that, okay, this hit from the U plane, this hit from the V plane, and this hit from the Y plane are all associated in the actual interaction. So yeah, so now looking at how message passing works with 3D space points and how we incorporated this within the model. So with our 2D message passing steps, right? As I sort of explained this message passing block in the original model, now that we have information from the U, V, and Y planes, we aggregate each of these message passing blocks. And the way we can do this is because the output of this step is always going to be the new learned node features. We take the node features from the outputted message passing blocks here, and we propagate that up to our 3D space point representations. So in this way, in this upward pass, for each space point, we're able to learn features from each of the planes. So now given sort of like all this concatenated information, we let the model learn basically and get a prediction on this space point. What does the model predict, like what class this space point should be? And on the downward pass, we're able to reach consistent conclusions across each of the corresponding 2D hits by just saying, okay, given this prediction on the space point model, we'll propagate it back down to the associated 2D hits. So this sort of space point, the introduction of 3D space points here is sort of a two-step process. We have our upward pass where we learn features from each plane, and then we have our downward pass where we use the new learn space point prediction to go from 3D to 2D and also enforce this consistency right here. And then we just incorporate this within the overall message passing iterations as an extra step. However, there is a caveat to this design based upon how these space points are made, which is on the upward pass, while each space point may have at most one contributing hit per plane, there's nothing stopping the fact from a 2D hit being used in multiple space points. Now, the reason why this is important is because in our downward pass here, if you look at this, these space points right here, I've labeled 4 space points as well as specific 2D hits that contribute to this or are associated with the space point. So we can see here for the U1 hit on the U plane, we actually have 4 different space points that link back to this hit. So on the downward pass, this causes issues because we really need to be careful about conflicts, because since a 2D hit can appear in multiple space points, we can't simply just add each of those features together, as that'll cause normalization issues in the graph. So there has to be some sort of way to pool these features together. So mean and max pooling were options that we tested, which is basically with respect to each class in each of these space point predictions, we can simply take the mean, or we can take the max features with respect to each class when down propagating that information back to the 2D hits. In addition, we can also introduce the idea of space point attention, which is basically similar to how the 2D network trained edge weights. We can also train edge weights with the 2D to 3D connections, and then use those weights to sort of inform, okay, let the model decide how important is the contribution of space point 1 back down to the 2D hits, or how important is the contribution of space point 2 back down to the 2D hits. So we can let the model learn which space points are more reliable and which space points deserve more attention when it comes to classifying each of these 2D hits back in their respective planes. So now that we sort of discussed the 2D and 3D, the 3D extension of the model, now I want to talk about sort of what the results look like with this. So first, the model summary that I'll show you right now has 16 total model configurations, which is just basically we went from 8 to 16 because each 2D model will have its own 3D variant. And the result that we get is a very mixed bag because of the fact that if you look at the results outlined in green, we have our best performing results are still in 2D. However, what's interesting to note is that outlined in purple is our 3D results, and that in 3D we did achieve our high consistency that we wanted, but there's a disconnect between the 2D and the 3D model, which is in the fact that our 3D results are very consistent, but lack in accuracy when compared to the 2D counterparts, as you can sort of see demonstrated by this table here. However, the 2D models have comparatively higher accuracy, but terrible consistency. So what's interesting here is that consistency in truth across these 3D space points is actually around 95 to 97%, which suggests that there is learnable information given the fact that the 2D consistency is already so low. So the question here is, how do we bridge this accuracy consistency gap that we have? And in describing the solution to this and what I've sort of dubbed the space point problem is understanding how our current networks currently works. So this is sort of like a simplified version of what this network is doing. So here we have each of the 2D planes working in parallel. We have our input features going into the edge network and then the node network. Same thing for the U, V, and Y planes. And all of this information is then concatenated. So then we can go through our upward pass where we take that concatenated information to 3D and then have our space point node network sort of learn and predict what classes or predict on the 3D features themselves. And then after we predict on our 3D space on the 3D space point level. We then have our downward pass where we go from the 3D space point level to basically copying that prediction to each of the U, V, and Y planes. And then, as I explained before, we incorporate this within our message passing iterations. And then this loop continues. Now, what's really important here and also responsible for sort of the accuracy consistency gap that we see is the fact that we enforce consistency here in the sense that when we predict on our 3D space points, we copy those features exactly to the U, V, and Y planes. So all of these features, as we go back to the beginning, will be exactly the same across all three planes. However, what's interesting and what actually worked a lot better was encouraging consistency versus enforcing it. And the only the major change that made this happen was this sort of crucial connection here. And what this does is instead of just forcing the 3D space point predictions to be copied to each of the planes, we actually allow the model to leverage our 3D informed prediction from the downward pass, in addition to our original 2D informed prediction here. So we concatenate those results and then we put them through separate linear layers on the U, V, and Y planes. So now instead of just enforcing the fact that all three, that the features have to be the same on all three planes, we let the model decide, okay, so here I have my 3D informed prediction. I also have my 2D informed prediction, and let the model decide and basically encourage the fact that now that you have the 3D context information, can you make better predictions on each of the separate planes? And the important case here is that these results are now distinct. They're not necessarily copies of one another. And this actually worked pretty well. So as a preliminary performance breakdown here, on the left, we have an efficiency matrix. On the right, we have a purity matrix. And then I'll give the actual absolute numbers as well. But basically on the left here, we want this diagonal to be 1. So we can see that we do pretty well with the HIP, MIP, and shower classes. And this is also on the simple labeling scheme. And probably the most worrisome classes here are the Michel and diffuse. But if you remember back to the dataset statistics, probably the largest reason for this is because they're so low in representation in the dataset. But basically to understand this matrix, we want the diagonal to be 1. And we can also consider the fact that here, basically, our model classifies 10% of Michel's in truth as actually showers. And then you can sort of see the same thing here, where 8.7% of Michel's in truth are actually classified as diffuse by the model. On the right, we have our purity matrix, which works a little bit differently in the sense that we still want our diagonal to be 1, but now for element ij in the matrix, class I classified by the model is actually class J in truth. So basically 7% of what we classified as Michel's in the model are actually MIP in truth, and 42% of what and 23% of what we classified as Michel in the model is actually shower in truth. So again, we sort of see that Michel and diffuse activity are probably most lowest performing classes, but that can also be explained by the fact that they're low, they're not as well represented in the data set. So as far as next steps go, so first, for future improvements, we want to continue developing the 3D model. So after the previously discussed change, that corresponding accuracy, the 3D model was able to reach 94% accuracy on sort of first pass results on the validation set. And as further proof of concept, this iteration of the model also had 96% consistency, which is also really exciting because even without enforcing consistency across all three planes, the model was able to learn it instead by just having that 3D context information available in addition to the 2D information that it had. And was able to bridge the accuracy and consistency gap by itself. In addition to those improvements, we have hyperparameter tuning, which consists of optimizing for the optimal number of message passing iterations, conversions given the number of epochs, and also batch size and the size of the hidden input dimension that we have at the beginning. And lastly, a direction we can also take is panoptic segmentation as well. So yeah, thank you. I hope this talk was useful and ready for any questions.
Okay, great. Thank you very much. Okay, questions in the room? Anyone on Zoom? So I had quick question. So the data that you're using to train all this is, you said on one of the slides you had something like 600,000 training. What is it? Oh, sorry. Yes, 651,000 graphs. So what does that correspond to in terms of like the number of tracks or hits or something? Because this is, I mean, this is different from, I guess, what I'm used to in terms of, fewer tracks per. Okay, just go ahead.
Yeah. So basically, the input data that we get does not have a specific graph structure. So I think a good example are these visualizations here. So you can think of this as so this is like the ground truth data that we're getting. So really we only have information on the hit level, where like we have the hits as well as their like classification in truth. And it's the edge forming schemes that we have here that basically determine our graph structure. So basically the inputs don't have a given graph structure. It's up to us to make to form the edges ourselves. The only thing that we're given is the nodes per graph, if that sort of makes sense. So the graph structure itself is sort of like a variable in and of itself.
Okay. So then how many events does this correspond to, or?
Yeah, so the training set, so this is basically the 651,135 graphs. One full interaction will just be a third of this number because we get 3 graphs per interaction from each of the planes.
Oh, okay. Okay. Okay, thank you very much. Any other questions? So if not, thank you again, Kushal.